Welcome to NARI SimCenter's Live Expert Tips. In this session, we will introduce you to the different methods supported in quoFEM for calibrating a model using experimental data. The example shown will use a calibration method that provides an estimate of the values of the model parameters as well as their uncertainty. Our expert today is Dr. Aakash, Bangalore, Satish. He is a postdoctoral scholar at UC Berkeley with the NARI SimCenter and a lead developer of the quoFEM application. Aakash received his PhD from the Department of Civil and Systems Engineering at Johns Hopkins University. His research interests include Bayesian estimation and model selection and averaging. Aakash, thank you for being here.
Thanks a lot, Matt. Thank you very much. Welcome, everyone. Thank you all for attending this session of the Live Expert Tips. In today's session, I'll be talking about calibrating a model using experimental data in quoFEM. So the process is generic, but we'll be focusing on how you can calibrate an OpenSees Material Model specifically through a couple of examples. So I'll first talk about model calibration, just briefly, just to give an overview of the idea of the process of deterministic as well as Bayesian calibration. And then I'll walk you through how to use quoFEM for calibration of simulation models. I'll discuss what is the workflow that we follow. So what do the users need to do in order to use quoFEM to set up a calibration analysis. And I'll briefly point out what are the different methods available in quoFEM for calibration. And then we'll go over two problems where I'll try to demonstrate how you can start from scratch with a model script that you have that can perform a material response simulation subjected to some experimental conditions. And if you have data from the similar experiment, how can you use that data in order to update or calibrate the parameters of your material model. So I'll talk about two cases within the time today. So just a brief intro to quoFEM, if people have not used quoFEM before. So quoFEM is the application developed by SimCenter, which combines uncertainty quantification and optimization with computational simulation models. We specifically started off with providing support for finite element models, but essentially you can work with a simulation model that can be defined in OpenSees, or it can be in PEEP, or it can be any Python script that defines your simulation model, or you can also have a custom finite element an analysis script that you are using. Even that can be supported through quoFEM. And I'll walk you through what are the different UQ engines or the optimization engines that are implemented in quoFEM as of now. And our philosophy is that you bring the computational model and we'll take care of the rest of the stuff. So we'll see how good a job we do in getting there. And these are some useful links. So this is the web page for the tool. So if you have not used quoFEM before, so you can find the application here. You can download that and use it. And our tool is extensively documented. So you'll find the documentation here in the link that I'm pointing to. And if you want to build your own version of quoFEM from the source code, so all the SimCenter applications are open source. So you can find all our source code at the NARI SimCenter GitHub repository. So you'll also find quoFEM source code in that GitHub repository. So you can build quoFEM from scratch. And if you want to develop new features or functionality, and if you want to contribute to a tool which where our mission is to make the tool widely available to the natural hazards engineering community. So you can be part of that, you can fork our repository and contribute to code to quoFEM. And we want to develop features that will be used by the community. So we are always welcoming feedback from the user community about what they want us to develop. we do have a list of things that we want to do, but this helps us prioritize our development process according to the need of the community. And yeah, there's another general point is you can, if you don't have a design safe account, you can sign up for a design safe account at this link. kofim provides kofim lets users run their analysis jobs on the computational infrastructure provided by the Texas Advanced Computing Center TAC. But in order to access that, you would need to have a design safe account. What is inside kofim? So as I mentioned, kofim tries to couple FEM applications with UQ and optimization methods. So this is just an overview of the different FEM engines supported and the different UQ methods that are currently incorporated in the tool, along with the algorithms that we are using that we are currently supporting for each of those methods. But today's talk, during today's talk, I'll try to focus on parameter estimation in a deterministic sense, as well as in a probabilistic sense, which is also called Bayesian calibration. So just an introduction to the problem of model calibration or parameter estimation. Let's say you have a computational simulation model, which is represented here by this function g of x. So that maps the inputs x to the outputs predicted by the model, which I'm calling as y predicted here. And one such relationship is shown here. So it can be coming from the result of some complex simulation. So essentially a simulation model is this, it's not an analytical model, it's where you use computational code to evaluate the response of your model given some input values. Now, as we observe here, so the response of the model is actually conditional on the value of the parameters of that model, which I'm calling by the letter theta here. So essentially what we have is a parameterized model or a class of models. And if we now look at the parameter space of that model, every point in this parameter space is corresponding to one specific model or one specific relationship between the inputs and the outputs. Now, if I look at other points in this parameter space, essentially that describes a different relationship between the inputs and the outputs, or a different mapping. So with this background, let's just take a look at what that, let's look at practically an example. So this is from the OpenSees documentation for the Steel 02 material model. So consider this material model, it has a number of parameters. So shown on the right-hand side is some value of the parameters that have been set. And then when the material response is evaluated for a given strain history, this is the resulting stress response. So this is the resulting hysteresis curve that we get. So this mapping between the strain input values and the stress output values predicted by the parameter depends on the values of the parameters of the model that we define here. Now, what happens if we change the value of those parameters? We get a different mapping. So in this case, the value of this parameter changed from 0.01 to a negative 0.01. So essentially it changed from a hardening material to a softening material and so on. So we can see that by changing the values of parameters, all of these are still Steel 02 material model, but within that material model class, it can represent a wide range of response depending on the value of the parameters that we have set. So this is that's the setting that we are in. So we have a parameterized model or a class of models. Now we have experimental data, so data available from some experiments. At the same value of the input parameters as what we have the data for, we can also run the simulation and obtain the corresponding predictions from the model for different parameters. There are different relationships. What we are interested in the problem of model calibration or parameter estimation is to now look in this parameter space and search for the right parameter value that sort of represents the relationship between the inputs and the outputs that we obtained experimentally from as described in the data set that we have here. So that is what we are looking for when we are doing parameter estimation. And the difference between the data and the predictions from the model is the prediction error, or it's also sometimes called the residual. So we want to, in some sense, like use the residual. So we want to minimize the residual or the discrepancy between or the prediction errors. So that is one particular approach to parameter estimation. So in this slide, I've just plotted the same residuals here. So we see that depending in all these cases, I'm assuming that the value of the inputs is fixed. So even though the predicted value of the y depends on the input as well as the parameter, I'm ignoring that dependence on the input because I'm using the same values of the input parameters and evaluating the model at different parameter values in order to get the corresponding residuals. We see that these are the kind of residuals that we get from this curve, from this figure, like given that data set, and for those parameter values. Now, in order to the deterministic approach to parameter estimation is to then make use of these residual values and one such and come up with some objective functions, which are also called loss functions. So these are functions of the parameters. One such objective function is shown here. In this objective function, the objective is the sum of the squared values of the residuals or the prediction errors. And in this deterministic approach, so this is a function of the parameter. So for each point in this parameter space, we can evaluate this function, and we would end up with something that looks like this. This is the contour plot of this function. Now, in deterministic estimation, the estimated value of the parameter would be that point in this parameter space, which minimizes this objective function. So this is what deterministic model calibration or parameter estimation means. It's essentially an objective optimization problem where we are trying to minimize some objective function. But there is another approach to model calibration. It's a probabilistic approach, and that's based on Bayes rule. Bayes rule is a probability law that can be derived from the axioms of probability. So it's not a theory, but it's a mathematical fact. So given some this is a form of Bayes rule, and I'll briefly describe what are all of the components here. But essentially, the denominator in Bayes rule turns out to be a constant for a given realization of the data set. So given some data values and given some assumptions about these two quantities, determine the denominator as a constant. So typically, we just look at this form of Bayes rule where the left-hand side is proportional to the product of these two terms on the right-hand side. So this constant number in the denominator is called the evidence. And each of these terms, I'll now try to describe them. So the first term here in blue is also called as the prior probability distribution. So in the Bayesian approach or in the probabilistic approach, in the Bayesian approach, all the unknown values, here our unknown is the parameter value, are treated as random variables. And the uncertainty in the parameter values is expressed through a probability distribution. So in this method, before we obtain any data or before we have any observations, based on any of our prior knowledge about the problem, we might have some estimate about what the parameter values could be. And we might also have some information about what could be the probability that this parameter takes on a particular value. And that is what is described in the prior probability distribution. So, for example, sometimes we might not have any information about the parameter value. So in that case, we might want to set a prior probability distribution that is that can go from negative infinity to plus infinity, and there are a normal distribution does that. So there are no lower bounds and upper bounds, and depending on how much information we have or how confident we are about what the parameter values could be, we can choose the parameters of that prior probability distribution to essentially the variance could be very small or very large. That means that depends on how much information we have about the problem. Similarly, if we have more information, like some parameter is always going to be positive, then we can use a prior probability distribution that has a lower bound, something like a log normal distribution, for example. Or if we know that there are both lower bounds and upper bounds on the parameter value, we can use some distribution which has both lower bounds and upper bounds, something like a beta distribution or something like that, or a uniform distribution. If all we have is that some information that the parameter values can take on any value in some range, and we don't know anything more about the relative frequency of or the relative probability likelihood of any of the parameter values within that range, then we can just use a uniform distribution to represent the prior. So essentially in this parameter space, so we have now set up a distribution across the parameter space. So this is the prior probability density. And then what we're interested in is getting this posterior probability density on the left-hand side, which updates our prior probability density using the information contained in the data to something which is called the posterior probability density. So typically, there is some information in the data which reduces our uncertainty about the value of the range of values that the parameter might take, or something like that. So typically, the posterior is somewhat narrower. In many cases, it might be quite narrow, depending on how much data we have. So if we have a lot of data, we can be quite confident in our estimate of the parameter values, and the resulting posterior would be very narrow compared to the prior. But if we don't have a lot of data, then we might still have high level of uncertainty about what the parameter values could be even after having data. So, but essentially, this is the target of our Bayesian parameter estimation exercise. Now, in order to get to the posterior, we need to use what is called the likelihood function here, and that is shown here. And so all these figures, in all these figures, I'm showing the contours of the prior probability density in blue, the posterior in red, in black, and the likelihood function in red. So in order to get to the posterior probability density, we need to compute the likelihood function, and we will be given some prior probability density to start with. So next we'll see how exactly we will compute the likelihood function. So right now I'm looking at the parameter space on the left-hand side, and I'm looking at the space of the outputs. So the output is a vector. So I've just plotted two components of that vector here. And we all know now that so any point here in the parameter space leads to a unique, not unique, but leads to some distribution of the, leads to some mapping of the, or some prediction of the output quantity. So here, these three parameter values result in these three, the corresponding predictions of the outputs as given by our mapping here. Now we have some data that I've represented in this space. Now what we want to find out is what is the likelihood function, that is the probability that any of these, the probability of the data given any of these parameter values. So in order to do that, we need to define a statistical model that is a probability distribution for how likely these data points are likely to have been generated by each of those points in the parameter space. In order to do that, so typically, and this is what we do in quoFEM also, we assume a normal distribution where given some mapping from this parameter space to the space of outputs. So we say that this predicted value of the from the model is the mean value of a normal distribution with some standard deviation, with some covariance matrix. So these are all vectors. So there's a mean vector which is given by the predicted value corresponding to a particular point in the parameter space. And then there is also a covariance matrix. Now that, so I've shown contours of this normal probability distribution in the space of the outputs, where the mean corresponds to the predictions from each of these parameter values. And then in order to get the probability of the data given the parameter value, what we need is the PDF of this. So it's essentially this lowercase p represents the probability density function. So all we need to compute is the probability density of this set of data points from this normal distribution. So that is how we get the likelihood function. And so for given a data set, this likelihood function is defined for every point in the parameter space. But the only thing is we need to evaluate what exactly is the prediction corresponding to every point in this parameter space. So we need to evaluate our computational model in order to actually sample values of these likelihoods. So that is the difficulty in Bayesian parameter estimation. So we would need several model evaluations in order to get the likelihood function. And then the prior probability density is defined by the users. So whenever you start off, you have to define the prior probability density, and you end up getting the posterior probability density. Now, quoFEM takes care of the likelihood calculation for you, so you don't need to worry about any of these things, but this is just the background information. What exactly do you need to do in quoFEM in order to do model calibration? So quoFEM has several panels. There are 5 panels. So in the first 4 panels, you define your problem. You set up the analysis that you want to conduct. So within the UQ panel, you essentially select what UQ method you want to use, whether you want to use probabilistic parameter estimation or deterministic and so on. In this FEM panel, you provide the computational model file. So this is the only thing that you need to, this thing and also the data is what you need in order to begin doing the, in order to use quoFEM for calibrating your model. So in the FEM panel, you provide what is the computational model that you want to use. And in the RV panel, you are essentially describing the prior, in the Bayesian case, you are defining the prior probability distributions. Or in the deterministic case, you are defining what is your search domain and where you want the search to begin from. So essentially, this is defining the inputs. And in the QI panel, you describe what are your response quantities of interest. That means what are the components of your output vector. So this is all you need to provide the information into quoFEM. And then once you do that, then you'll click the run button or the run at design check button. And then quoFEM goes to the backend. It performs all of these calculations, computes the results, and then it will return the result back to the user interface. And the results will be displayed in the results panel, where there are some options to summarize and visualize the results and to save the results of your analysis. Now, the way the inverse problem is set up in quoFEM is that you can use the same computational model for solving the forward problem. That means if you just want to propagate uncertainty through your model, you can do that, or you can use the same model script in order to estimate the parameters of your model given data. So there are a few methods which are implemented right now in quoFEM. I'll just briefly mention what they are. So these 2 methods are used for parameter estimation. These are deterministic optimization algorithms. And we are using Dakota to support these algorithms. Essentially, they use the Newton's method to search your parameter space for the optimum parameter values to minimize the sum of the squared errors. But these are specialized, and they make use of the special structure of the objective function, which is the sum of squared error terms. So for that structure, there can be an approximation that can be made to the Hessian. So you don't need, so in order for all of these algorithms to work, you need to evaluate the model, you need to evaluate the gradient, and you also need to evaluate the Hessian. I mean, by you, I mean the algorithm does all of that for you. You don't have to do these. But based on the special structure of this problem, an approximation can be made to the Hessian so that reduces the computational burden a little bit. So these are specialized algorithms for solving nonlinear least squares minimization problems. Now, there are two options for solving the Bayesian calibration problem. DREAM is an MCMC-based algorithm that is, again, implemented in Dakota and supported through quoFEM. Another algorithm is the TMCMC algorithm. So this is developed in collaboration with our team at UCSD, UC San Diego, Anderson Center. So this is just a brief overview of the different methods that are available in quoFEM. Now, the more interesting part and the more practical part is, okay, what is the general process? How do you calibrate a model? So essentially, you have OpenSees model script that can perform one simulation of the material response. Now, so that is the starting point. And then within the script, so quoFEM requires that you write the results of the simulation, that is the prediction, the Y prediction for a given value of the theta. So you write the result of the simulation to a file called results.out. So this is so that quoFEM knows where to look for the results once an analysis is conducted during the calibration process. And then once you have this, in order to so you will then declare the parameters of the model that you want to calibrate as variables. I'll give a demo of what I mean. And then we will use the special keyword called tset instead of set to let quoFEM know that some of these variables that you declare here are actually the calibration parameters. So these are the things that you need to do in order to prepare your model script for doing parameter estimation using quoFEM. So that's all. All you need is a model script that can run one simulation. And then you would also need the data in order to do calibration. So you will provide the calibration data in a separate file. And in each row of this file, you'll provide the data from one experiment. So these are the two things that you need. Now let me jump into an example. So in this problem, our objective is to calibrate the STEEL02 material model parameters using some cyclic stress strain test data obtained from experiments. So these are this is the strain history that is used as input that is supplied to the model script. And then that model script performs one simulation of a cyclic stress strain test. So essentially, it evaluates what is the corresponding stress values given these strain values. And if you look at only the output quantity, so the blue line is the data, and the red line is one such prediction from a parameter value after calibration has been done, after deterministic calibration has been done through quoFEM. So this example is actually available through quoFEM. Now let me quickly jump into quoFEM. And Matt, can you see my screen? Can you see quoFEM?
Yes.
Okay. So within quoFEM, there are a lot of examples shipped with the tool. So the last two files here, the last two examples here refer to doing material model calibration using Bayesian method or using the deterministic method. So if I just click on any of these provided example files, it will populate the required fields. It will set up the problem for you within quoFEM. So there are several panels in quoFEM. These are the same 5 panels that I was referring to in a previous slide. So within the UQ panel, you choose what method you want to use. So this is the TMCMC algorithm that I was mentioning before. And you specify some of these quantities that are required. So in this case, since you're doing Bayesian calibration, you need to characterize your posterior in terms of samples drawn from the posterior. So how many samples you want to draw from the posterior is one input that you need to provide here. And now this is a seed which is given for reproducibility. So if you want to run the same, if you want to reproduce the results again, if you set the same seed and run the same analysis again, you'll get the same results. And within this panel, you also provide the calibration data file. I won't talk about the optional. And then within the FEM panel, you provide the path to a tickle script. So this tickle script performs one material test that I described before. Now these are in the RV panel, you define what are your input variables. So in this case, the Steel 02 material model has a lot of parameters. You are trying to calibrate 7 parameters, and you define what the prior probability distribution for each of those parameters should, what is the prior probability distribution you want to use here. And one feature here is that you can see the PDF of the parameters that you chose here. So for example, if you set a normal distribution with some mean and some, I'm just typing in some numbers here. You can visualize the PDF. So the normal distribution is unbounded and so on. So there are several distribution options here. Let me reset everything. So, and then finally, in this panel, you define what are your output quantities of interest. So I'm looking at the stress history in this example. So that is of a length of 342 because there are 342 data points in my input. And then when you click on the run button or the, so kofim will perform the analysis in the background. So if you click on the run a design safe button, you can log into, oops, this side. I'll look into it later. So you can log into design safe and perform the same analysis on the high performance computing setup facility attack. Now let me walk through what this script looks like. So essentially, you have one tickle script that can perform, that can simulate one material test. So within all of your material model calibration problems, so in your OpenSees tickle script, there will be a line where you define the material model that you want to use. So instead of so the first step is to declare the parameters that you want to calibrate as variables. That means you have to provide you have to set the values of these variables here. And then of the variables that you want to calibrate, you should use the keyword pset instead of the keyword set. So that is all you need to do. And now you have to also ensure that you write the results to a file called results.out. And in this case, I'm reading in this strain values from this file with this file name, and I'm simulating a material test. Essentially, I'm looping over the strain history for each strain in the strain history. I'm computing what is the corresponding stress, and that stress quantity is written to this out file, which is results.out. So this is it. So these are the only steps, only changes that you had to do in order to prepare your script for analysis with kofim for material model calibration. So another file that you need to see is the data file. Let me quickly pull that up. So within this data file, you provide the strain values that you will be using for the analysis. And yeah, those are the things that you need to do, and you can run the example through kofim once that is ready. Now I'll quickly move on to another example. If I can find my slides back. Okay, so another example is a more complicated case where instead of just having a uniaxial material, we want to calibrate an n-dimensional material model. So this material model is actually representing the behavior of sand. And we have experimental data, which is coming from a cyclic simple shear test. So it's a cyclic test that is experimental setup. And we want to simulate that experiment computationally in OpenSees. So we have a model script that performs a single element simulation that tries to simulate the cyclic simple shear test. Now these so in order to simulate the response of the material, I'll be using the PM4 sand material model, which is as this so this is from the OpenSees documentation. So the PM4 sand material model has been implemented in OpenSees by Longchen and Pedro Arduino at University of Washington. It was developed by Boulanger and Siotopoulou. Now this material model has 24 parameters, and in the same page there is a script here which performs a simulation of a 2D undrained cyclic direct simple shear test using one element. So this is the same model script that is the starting point for the calibration exercise of the sand response. So the one unique feature of the PM4 sand material model is that it is capable of representing liquefaction behavior of sand. And so as part of some RU program during the last summer, so we worked with an undergraduate student and did some research where we did some sensitivity analysis and calibration of the material model. And I'll not be discussing sensitivity analysis, but during the baseline calibration, so we had data from experiments, which is shown in this thick solid line here. And then we performed baseline calibration. And this is on the left-hand side. This shows the posterior distribution of the 3 parameters out of the 24 that we calibrate. Excuse me. So we say that after informing, so the blue density here represents the prior probability density. And after being informed by the data, we see that the posterior is much narrower in this case. And then once we draw samples from the posterior, we can then propagate that uncertainty in the model parameters through, in this case, through a soil column model where there are 3 layers of soil, and then one of the layers is PM4 sand, and which is underneath the water table. And when this soil column is subjected to earthquake, ground motion in the base, this sand undergoes liquefaction, and the resulting response is shown on the right hand side. So what do we gain by doing basin parameter estimation? So since we have uncertainty in the posterior probability distribution of the parameters, so that means we can also propagate that uncertainty through the forward propagation part of this problem, and we can end up getting estimates of how much uncertainty there is in the lateral spreading of the soil column. So this is a profile of the lateral displacement of the soil column when it is subjected to this ground motion. So this was the problem, and I'll quickly show again. So this is the analysis script, which is which performs. So which is based off the script that I showed in the OpenSees documentation. So essentially that script performs a simulation of the direct simple shear test, cyclic direct simple shear test. So I have split that file into 2 parts, and here I just want, for the sake of this demonstration, I just wanted to show that these are the 24 material model parameters, and of these parameters I'm just calibrating these 3 model parameters, so that those I will use the pset keyword to indicate to kofim that those are the 3 parameters that I want to calibrate. And the unique thing, or the different thing in this example compared to the previous one is that each of those data points is coming from a different simulation. So in order to get the 6 data points, the 5 data points here, so we have to perform a simulation of the direct simple shear test at different values of the shear stress. So essentially that is all I'm doing here. So I'm looping over a value, a CSR value in this CSR list, and I'm running and I'm performing a simulation of the experiment. Now, I return the results to this results file. So this is the setup for the PM4 sand model calibration problem. And I'll walk you through some of the results and what we can get out of Bayes rule by using Bayesian calibration. So in this slide, I show a plot of the samples from the posterior probability distribution. So this is the joint posterior probability distribution of these parameter values. So what this figure shows is that there is a lot of uncertainty about the parameter value. So we see a wide range in the posterior here. Now, why is this? So this is because in order to get the cyclic strength curve, which is the data from the experiment, so all that is done is we conduct a simulation of the experiment and then just count how many number of cycles it took before the onset of liquefaction. And the onset of liquefaction is just defined as using some shear strain threshold level. So whenever the shear strain reaches a threshold value during the simulation of the cyclic test, that is considered to be the onset of liquefaction. So since that is the only data point that we are using, we are not looking into how the actual hysteresis response during the experiment is simulated. So since we're only interested in how many number of cycles it took, it might have taken the same number of cycles to reach that strain threshold value in several ways. So each of these points is sort of saying that even if you set any value of these parameters from this point, you'll end up getting this similar values for the number of cycles to the onset of liquefaction as that obtained during the experiment. So that is why we see a lot of wide. This problem is called lack of identifiability of the parameters. So you cannot uniquely determine a single parameter value, but all of these parameter values are giving you similar response as that obtained in the experiments. So this is one advantage of Bayesian estimation. So any of these values could have produced the data that you saw in the experiment. So Bayesian inference, Bayesian estimation lets you propagate, lets you keep all of that uncertainty. So since any of those could have produced the results. Now in this figure, I'm showing the resulting prediction of the cyclic strength curve. So these red triangles are the data points from the experiment. And this blue patch is the range of all the predictions of the cyclic strength that we obtained from the posterior sample values of the parameters. So each of those sample values of each of those points produces a particular cyclic strength curve. And the range of the predictions from the posterior more or less sort of covers the range of scatter in the data that we observe here. So that's something good. And another thing to observe is once we have all of these predictions, we can take the mean value of all of those predictions. And that corresponds to the solid blue line in the curve here. And previously, for the same data set, another calibration had been done sort of deterministically and sort of manually, I guess. So they had obtained this fit with some root mean square error of 2.59, and the mean of our predicted cyclic strength has a smaller root mean square error compared to. So these are some of the advantages that you can get by using Bayesian estimation, by doing Bayesian parameter estimation. Now, again, all of those samples were used as input to the soil column model that I described in one of the previous slides. And this is the range of predictions that we obtained for the lateral spreading. Now, at the surface, this shows what is the histogram and the density estimate of the lateral spreading, the amount of lateral spreading at the surface. So we can get we can quantify the uncertainty in these predictions by using Bayesian parameter estimation. So that's why we use Bayesian parameter estimation in this case. Now, in this slide, I'm just making a comparison of how much uncertainty there is in the predictions from the prior, which are shown in these gray lines, versus how much that uncertainty has reduced as a result of updating our model and informing using the data to inform our estimate of the parameter values. So it's the same curve as before, but just the predictions from the prior also shown for comparison. So yeah, just to wrap up, this is my last slide. So how do you calibrate an OpenSees material model using quoFEM? So start with the model script. You bring the models that can perform one simulation of the material response, and then you do the tweaks to that model script that I walked through. So write the result to a file called results.out and let quoFEM know that which of those parameters of the model you want to calibrate by using the pset keyword, and then provide the calibration data in a separate file to quoFEM. So yeah, these are some upcoming features of quoFEM that we plan to implement. We plan to implement global sensitivity analysis. So already you can do global sensitivity analysis, but we want to work on supporting that for high dimensional outputs. And then we are also working on, so Sangri, another postdoc in the Sim Center, is working on implementing multi-fidelity surrogate modeling with adaptive design of experiments where you can generate data also. And another thing that we're working on is model class selection and averaging. When you don't have a single model, but so when all you have is a set of data and there are competing models which can represent, which has all the features, which can represent all the features of the data set. Now, which model should you choose? So that can be answered in several ways, and in the Bayesian way, you can do Bayesian model selection and averaging. This is again something we are working on. And as I mentioned before, so you can please tell us what you would like to see in quoFEM by making feature requests in our Sim Center forum, and you can report any bugs that you find in our code there. And yeah, you can also reach out to us for any questions that you have. Yeah, that brings me to the end of my presentation. Thanks a lot.
Aakash, thank you very much for the presentation. Two very interesting examples. I think they're both informative about how somebody might go about adapting an existing material model that they have to benchmark against an experiment. So this is fantastic. There's a question about quoFEM and its ability to use finite element packages other than the plain vanilla OpenSees. And in particular, right, they're curious about using OpenSees SP.
Right.
Are you familiar with how somebody might use OpenSees SP as the finite element package instead of OpenSees?
So within quoFEM, so that you can set, there is something called the preferences panel here. So quoFEM ships with OpenSees, and if you don't want to use the OpenSees version that is shipped with quoFEM, if you want to use another flavor of OpenSees, for example, then you can just select on this custom and you can point to the OpenSees executable that you want to use instead of the one that comes shipped with quoFEM. So that way, I feel you can use another version of OpenSees rather than the one that comes as default. I don't know exactly how SP and MP are different from OpenSees. I can't comment on that aspect of it, but if you want to change your OpenSees executable, you can do that.
Fantastic.
In the preferences panel.
Thank you, Aakash. In the light of time, I think that we'll go ahead and wrap up, but I want to say thank you for the attendees and the questions provided. Thank you to Aakash for a great presentation. And this concludes today's live expert tips with the NARI Sim Center. I encourage you to check in on our webpage, simcenter.designsafe-ci.org, to look for additional upcoming live expert tips. I also encourage you to subscribe to our SimCenter newsletter, where we'll remind you about other events like this offering. And you subscribe to our newsletter through our webpage. So please look there. Hopefully you've been inspired to pick up the example that Aakash shared and adapt it to its capabilities to your research or your work. And thank you for attending.